It has been observed that there is an increase in do-it-yourself threads. While interest in building feeders is commendable, it can present challenges for less experienced members. A proposed solution is to incorporate a motor feeder calculation tool into the registration form. This aims to filter out individuals who may not possess the necessary expertise for complex do-it-yourself projects. However, it is crucial to consider that everyone starts somewhere, and discouraging learning should be avoided. An alternative approach involves creating a comprehensive sticky thread or a dedicated wiki page. This resource would offer fundamental information about do-it-yourself projects, including guidance on selecting projects that align with skill levels and accessing relevant resources for successful completion. This approach allows individuals to educate themselves before committing to a project. Exploring additional solutions to address this issue is also encouraged. When undertaking do-it-yourself electrical projects, particularly those involving motor feeders, it is essential to prioritize safety and adhere to established electrical codes and standards. A motor feeder supplies power to a motor, and its proper design and installation are crucial for ensuring the motor's safe and reliable operation. Firstly, determine the motor's full load current, often referred to as FLA. This value is typically found on the motor's nameplate and represents the current the motor draws when operating at its rated horsepower and voltage. Secondly, calculate the minimum feeder conductor ampacity. According to the National Electrical Code, or NEC, section 430.22, the feeder conductor supplying a single motor must have an ampacity not less than 125% of the motor's full load current. This oversizing accounts for the motor's starting current, which can be significantly higher than its running current. Thirdly, select the appropriate conductor size based on the calculated ampacity and the type of insulation used. NEC Table 310.16 provides ampacity ratings for various conductor types and sizes at different operating temperatures. Ensure that the selected conductor size can handle the calculated ampacity at the expected operating temperature. Fourthly, determine the size of the overcurrent protection device, such as a circuit breaker or fuses. The overcurrent protection device protects the feeder conductors and the motor from overloads and short circuits. NEC section 430.52 provides guidelines for selecting the appropriate overcurrent protection device size. For motors with specific starting characteristics, such as high immerse current, time delay fuses, or inverse time circuit breakers may be necessary to prevent nuisance tripping during motor starting. Fifthly, consider voltage drop in the feeder conductors. Excessive voltage drop can negatively impact the motor's performance, causing it to run inefficiently or even stall. NEC section 215.2 provides recommendations for limiting voltage drop in feeder circuits. To minimize voltage drop, select conductors with a larger cross-sectional area or reduce the feeder length. Sixthly, properly ground the motor and the feeder circuit. Grounding provides a low impedance path for fault currents, helping to protect personnel and equipment from electrical shock. NEC Article 250 provides detailed requirements for grounding electrical systems. Ensure that the motor frame is properly grounded to the equipment grounding conductor in the feeder circuit. Seventhly, use appropriate wiring methods and enclosures for the environment in which the motor feeder is installed. Factors to consider include moisture, temperature, and the presence of corrosive substances. NEC Chapter 3 provides requirements for various wiring methods and enclosures. Eighthly, install a disconnecting means within sight of the motor and the controller. The disconnecting means allows for safely to energizing the motor and the feeder circuit for maintenance or repair purposes. NEC section 430.102 requires a disconnecting means to be readily accessible and capable of being locked in the open position. Ninthly, properly label all components of the motor feeder circuit, including the disconnecting means, overcurrent protection device, and conductors. Labeling helps to identify the circuit and its components, making it easier to troubleshoot and maintain the system. Tenthly, consult with a qualified electrician or electrical engineer to ensure that the motor feeder design and installation comply with all applicable codes and standards. Electrical work can be dangerous, and it is important to have the expertise of a qualified professional to ensure safety and compliance. Understanding motor feeder calculations is crucial for ensuring the safe and reliable operation of electrical systems that power motors. The National Electrical Code provides comprehensive guidelines for sizing conductors, selecting overcurrent protection devices, and grounding motor circuits. Firstly, determining the motor full load current, or FLA, is the foundation of any motor feeder calculation. This value, typically found on the motor's nameplate, represents the current the motor draws when operating at its rated horsepower and voltage under full load conditions. The FLA is essential for calculating the minimum ampacity of the feeder conductors and for selecting the appropriate overcurrent protection devices. Secondly, calculating the minimum feeder conductor ampacity is a critical step in ensuring that the conductors can safely carry the motor's current. According to NEC Section 430.22, the feeder conductors supplying a single motor must have an ampacity of at least 125% of the motor's full load current. This oversizing accounts for the motor's starting current, which can be significantly higher than its running current. For example, if a motor has an FLA of 20 amps, the minimum feeder conductor ampacity would be 20 amps times 1.25, which equals 25 amps. Thirdly, selecting the appropriate conductor size based on the calculated ampacity is crucial for preventing overheating and ensuring reliable operation. NEC Table 310.16 provides ampacity ratings for various conductor types and sizes at different operating temperatures. It is important to choose a conductor size that can handle the calculated ampacity at the expected operating temperature. For example, if the calculated ampacity is 25 amps and the conductors are rated for 75 degrees Celsius, a number 12 American wire gauge or AWG copper conductor with an ampacity of 25 amps would be suitable. However, if the conductors are rated for 60 degrees Celsius, a number 10 AWG copper conductor with an ampacity of 30 amps would be required. Fourthly, determining the size of the overcurrent protection device, such as a circuit breaker or fuses, is essential for protecting the feeder conductors and the motor from overloads and short circuits. NEC Section 430.52 provides guidelines for selecting the appropriate overcurrent protection device size. The type of overcurrent protection device and its trip characteristics must be carefully considered to ensure proper protection without causing nuisance tripping during motor starting. For example, for a motor with an FLA of 20 amps, the maximum allowable overcurrent protection device size for an inverse time circuit breaker is typically 250% of the FLA, which would be 50 amps. However, the actual size may need to be reduced based on the motor's specific starting characteristics and the breaker's trip curve. Fifthly, considering voltage drop in the feeder conductors is important for maintaining optimal motor performance. Excessive voltage drop can reduce the motor's torque and efficiency, leading to overheating and premature failure. NEC Section 215.2 provides recommendations for limiting voltage drop in feeder circuits. It is generally recommended to limit voltage drop to no more than 3% in the feeder circuit and no more than 5% in the combined feeder and branch circuit. To minimize voltage drop, conductors with a larger cross-sectional area can be used, or the feeder length can be reduced. Sixthly, properly grounding the motor and the feeder circuit is critical for safety. Grounding provides a low impedance path for fault currents, helping to protect personnel and equipment from electrical shock. NEC Article 250 provides detailed requirements for grounding electrical systems. The motor frame must be properly grounded to the equipment grounding conductor in the feeder circuit. The size of the equipment grounding conductor is typically determined based on the size of the ungrounded conductors in the feeder circuit. Seventhly, using appropriate wiring methods and enclosures for the environment in which the motor feeder is installed is essential for protecting the conductors and equipment from damage and ensuring safe operation. Factors to consider include moisture, temperature, and the presence of corrosive substances. NEC Chapter 3 provides requirements for various wiring methods and enclosures. For example, in wet locations, conductors must be installed in waterproof conduit or cable with appropriate fittings. Eighthly, installing a disconnecting means within sight of the motor and the controller is required for safely de-energizing the motor and the feeder circuit for maintenance or repair purposes. NEC Section 430.102 requires a disconnecting means to be readily accessible and capable of being locked in the open position. The disconnecting means can be a switch or a circuit breaker that is rated for the motor's full load current. Ninthly, properly labeling all components of the motor feeder circuit, including the disconnecting means, overcurrent protection device, and conductors, is important for identifying the circuit and its components, making it easier to troubleshoot and maintain the system. Labels should be durable and legible, and they should clearly indicate the function of each component. Tenthly, consulting with a qualified electrician or electrical engineer is recommended to ensure that the motor feeder design and installation comply with all applicable codes and standards. Electrical work can be dangerous, and it is important to have the expertise of a qualified professional to ensure safety and compliance. By following these steps and adhering to the NEC guidelines, individuals can safely and effectively perform motor feeder calculations for do-it-yourself projects. However, it is important to remember that electrical work should only be performed by qualified individuals who have the necessary knowledge and experience. Understanding the different types of motor starters is essential for selecting the appropriate starter for a specific motor application. Motor starters are devices used to start and stop electric motors, and they also provide overload protection to prevent motor damage. Firstly, across-the-line starters are the simplest and most common type of motor starter. They connect the motor directly to the power supply, providing full voltage to the motor windings. Cross-the-line starters are suitable for applications where the motor can handle the inrush current associated with starting at full voltage. Secondly, reduced voltage starters are used to limit the inrush current during motor starting. These starters reduce the voltage applied to the motor windings during the starting period, gradually increasing the voltage to full voltage as the motor accelerates. Reduced voltage starters are used in applications where the inrush current of an across-the-line starter would cause voltage dips or other problems in a power system. Thirdly, auto-transformer starters are a type of reduced voltage starter that uses an auto-transformer to reduce the voltage applied to the motor windings during starting. Auto-transformer starters provide a smooth and stepless reduction in voltage, resulting in lower inrush current compared to other types of reduced voltage starters. Fourthly, power winding starters are another type of reduced voltage starter that uses a special motor with two or more separate windings. During starting, only one winding is energized, reducing the inrush current. Once the motor reaches a certain speed, the remaining windings are energized, bringing the motor up to full speed. Fifthly, Y-delta starters are a type of reduced voltage starter that uses a special motor with windings that can be connected in either a Y or a delta configuration. During starting, the motor windings are connected in a Y configuration, which reduces the voltage applied to each winding. Once the motor reaches a certain speed, the windings are reconnected in a delta configuration, applying full voltage to the windings. Sixthly, solid-state starters use electronic components, such as silicon-controlled rectifiers or SCR, to control the voltage applied to the motor windings during starting. Solid-state starters provide precise control over the motor's acceleration and deceleration, and they can also provide additional features such as soft starting and stopping. Seventhly, variable frequency drives or VFD are the most advanced type of motor starter. VFD control both the voltage and frequency applied to the motor windings, allowing for precise control over the motor's speed and torque. VFD are used in applications where variable speed control is required, such as pumps, fans, and conveyors. Eighthly, selecting the appropriate motor starter depends on several factors, including the motor's horsepower, voltage, and starting characteristics, as well as the requirements of the application. Across-the-line starters are typically the most economical choice for small to medium-sized motors that can handle the inrush current associated with starting at full voltage. Reduced voltage starters are used for larger motors or applications where inrush current is a concern. VFD are used for applications where variable speed control is required. Ninthly, it is important to consult with a qualified electrician or electrical engineer to determine the appropriate motor starter for a specific application. Motor starters must be properly sized and installed to ensure safe and reliable operation. Tenthly, understanding the different types of motor starters and their applications is essential for selecting the right starter for a particular motor. Properly selected and installed motor starters can improve motor performance, reduce energy consumption, and extend motor life.